Unless you know the orientations of d orbitals, how interaction with the ligands is occurring, you will not understand. Therefore, let us know what are those d orbitals, how are they aligned or oriented, what are their shapes. See here, the 5 d orbitals are represented. One by one, let us see. dz square orbital. The orbital, the lobe is along z axis, and if you observe, as like a ring is on the Saturn satellite, or the donut is a food atom, or you can say medu vada, their ring kind of the structure remains. Such kind of the ring is there around the z axis or along x and y. So partly it has a orientation towards x and y, and major orientation is towards z axis. Let us consider by yellow color positive wave function and by brown color negative wave function is represented. Wave function is not important at this moment, but orientation, shape is important. What's the understanding of the dz square orbital? dz square orbital is oriented more towards z axis and partly towards x and y. See the second orbital. dx square minus y square. Lobes are along x and y axis, perfectly along axis. So two opposite lobes are with yellow color and other two opposite lobes are with brown color. Are you understanding dx square minus y square orbital? See the third orbital. That's a dyz orbital. The yz plane, if I consider towards you the y-axis and upside z-axis, then this is yz plane. The lobes will be in between y and z axis. Two opposite lobes, yellow colored lobes are between y and z. Accordingly, brown color opposite lobes are also between y and z. So lobes are making angle 45 degree to axis, to y-axis and z-axis. So lobes are in between axes. That's a dyz orbital. See the next orbital, dxz. Here also lobes are in between axes, but axes are x and z. Means x-axis to our left, right, and z-axis upside, the positive x and the positive z. Then in between x and z, there will be the lobe. Similarly here lobe. So what is the angle made by this lobe to the axis? It is 45 degree to x and z axis. So yz orbital is in yz plane, xz orbital is in xz plane. Likewise now last orbital, xy orbital, it will be in xy plane. X-axis, y-axis. So in between x and y there will be the lobe. Similarly other three lobes will be there. What will be the angle by the lobe to any axis, x-axis or y-axis? It will be 45 degree. What you are finding? Last three orbitals, dxy, dxz, dyz, those are in between axes. And first two orbitals, dx square minus y square and dz square, those are along axis. dz square, majority contribution is along z axis and partly along x and y. dx square minus y square, completely along x and y axis. dyz in between y and z, dxz between x and z, dxy between x and y orbitals. That's the understanding of these orbitals. This is very important. If this imagination, if these shapes are clear to you, then next part, interaction and accordingly energetics of various orbitals will be perfectly clear to you. To make this concept clear, with this model I explained to you, so that concept will be more clear. Let us consider the red bonds, z-axis, positive z, negative z direction. Towards your right and left is x-axis, yellow color x-axis, positive direction, negative direction. Towards your side and my side, y-axis, positive direction of y and negative direction of y. Let us understand these orbitals again. First orbital is dz square orbital. The lobes are along z-axis, see here, plus as like donut, the ring structure is there. That ring structure is in this xy plane. Actually dxy, dyj, dxz, three kinds of orbitals are there, three pairs are possible. Likewise As dx square minus y square is there, there should be dz square minus y square, there should be dz square minus x square. But those are not there. Combination of that dz square minus y square and dz square minus x square is our actually dz square orbital. Other component we are not mentioning, but it is there. So that ring kind of structure is in xy plane. So if I have to understand this orbital is more along z axis and it is there in xy plane also. Not exactly x and y direction, but in xy plane. Is that dz square orbital clear? Second orbital is dx square minus y square orbital. It is perfectly along x and y axis. So lobes will be along x axis and along y axis. So it is in this xy plane and along x and y axis. Now see the third orbital, dyz orbital. Where is our y axis? Yes, towards you and towards means y. Where is z? Up and down. So in between y and z here, in between, if I rotate that here will be the one lobe of dyz. Opposite lobe will be here. Next lobe, opposite lobe. So likewise, in between y and z, the lobes will be there. So if I cut that yz orbital, the lamina will be in this way. It is a yz plane. Is dyz orbital clear? It is not along y and z axis. It is in between y and z axis. Now see the fourth orbital. That's a dxz orbital. Now it will be very clear. It is x-axis and z-axis. In between x and z, one lobe, opposite lobe, third lobe, last lobe. So in between x and z. So what is the angle made by those orbitals, those lobes to the axis? So to z-axis 45 degree, to x-axis also it will make 45 degree angle. So it is in which plane? It is in xz plane. This plane is perpendicular to previous yz plane. When water molecule we studied at that time, these planes we have studied. Same concept we have to apply here. Now last orbital, that is xy orbital, dxy orbital. It is your x-axis and y-axis. Where will be the lobe? Along x and y? No, in between x and y. So lobe will be between x and y, making 45 degree angle to x-axis or to y-axis. Similarly, opposite lobe, third lobe and last lobe. Likewise, the lobes will be in xy plane. Is this dxy orbital clear? So what crystal field theory considers? Surrounding ligands whichever are there as point charges. Second point, there is a electrostatic force of interaction, ionic interaction between point charges, negative point charges to the ligands and positively charged metal ion. The d orbitals of free metal ions are degenerate. And in spherically symmetric hypothetical field, interaction will be there, negative field of ligand and electrons of the d orbitals. In spherical symmetric hypothetical field, degeneracy is maintained. But in our geometries, here octahedral, in other geometries, tetrahedral, square planar, triangular, trigonal, bipyramidal, any geometry you consider, the interaction will not be uniform as is there in spherical symmetric hypothetical field. Therefore, energy change will occur in the orbitals. If you know the shapes, then energy change you will understand. What are the shapes? dz square orbital along z-axis and in xy plane. dx square minus y square orbital along x and y axis. dyz orbital in between y and z. dxz orbital between x and z. dxy between x and y. That's the understanding. If you are with, then basis of crystal field theory is clear to you. Let us apply this basis of crystal field theory in order to describe the various geometries. While applying crystal field theory to various geometries, the shapes of orbitals are important. By the way, contribution of axis to the orbital also is important. Means, for example, dz square major contribution is of z orbital, or it has z component. xz has x and z component. dz square, dyj, dxz, these are orbitals with z components. In that, dz square extremely high z component. xz and yz, it is a pair having the same z component. Other way, x square minus y square, x and y component. xy, x and y component, but xy means lobes are in between the x and y axis. So in generally, the z component possessing orbitals and non-z component possessing orbitals. Likewise, we can divide the orbitals. Then perfect orientation also is important. Let me consider square planar arrangement of the metal and ligand in this way. What I am considering, x-axis, it is our y-axis, and perpendicular to x and y is z-axis. Let us form two sets, the z component possessing orbitals and non-z component possessing orbitals. Ligands are along x and y axis. So x and y axis component possessing orbitals will experience strong interaction, strong repulsion. The energy has to increase. Let us see which are the non-z component possessing orbitals. Right, dx square minus y square and dxy. Let me talk one by one. Dx square minus y square. The lobes are directly along x and y axis. So that orbital will experience strong interaction. Let us see interaction for dxy orbital. Dxy orbital lobes are between x and y. So makes 45-degree angle. Makes 45-degree angle. The lobe makes 45-degree angle. This lobe makes 45-degree angle. So direct interaction is not there. Interaction is there, but direct interaction not there as is in dx square minus y square orbital. So among these two, which orbital will increase in energy? Yes, dx square minus y square orbital will increase in energy. See that highest energy orbital dx square minus y square. Below that dxy orbital. And in order to maintain barycenter the same, other, that's the z component possessing orbitals, will decrease in energy. Now which orbitals are there which are with z component? Three orbitals are there, dz square, dxz and dyz. Dxz and dyz are very similar, same kind of interaction will be there. So I divide them in two parts, dz square and this non-axial dxz and dyz. Let me talk about dz square. The dz square orbital major lobes are along z axis, but the donut shape is there, no? Donut region is there, that is in xy plane. That donut region will experience interaction, repulsion it will experience. So its energy relatively will be higher or lower. Let us compare. If I consider other dxz orbital, it is x-axis and z-axis. Between x and z, it makes 45-degree angle to the ligands. So direct interaction is not there. Because of dz square donut shape, donut arrangement, relatively dz square orbitals experience more repulsion than dxz and dyz. So what do you think? Whose energy will be higher? dz square or dxz and dyz? Right, dz square. So see the energy sequence at lower level to maintain barycenter the same. dz square will be of higher energy, and below that dxz and dyz orbital. It is a square planar arrangement. Let us see the next part, trigonal bipyramidal arrangement, coordination number 5. Actually one more arrangement is possible, but let us see TBP in next part. As a homework question for you, in square planar complexes, out of 5D orbitals, which orbital experiences maximum repulsion? Means whose energy is highest? Write your answer in comment box. Yes, in trigonal bipyramidal arrangement, coordination number is 5. How can I consider the model for trigonal bipyramidal? See, I consider it is a z-axis, x-axis, y-axis towards you, towards me, but no ligand is approaching along y-axis. So two ligands are there along z-axis, one ligand is there along x-axis. This ligand is there making angle 30 degree to y-axis. A green ligand is there which is making angle to y-axis 30 degree. It's our consideration of trigonal bipyramidal arrangement. Now those 5 d orbitals we can divide in 3 parts. One, dz square, major portion along z-axis. Second part, dxz and dyz. Those have z component, makes 45 degree angle to z-axis. Third set, dx square minus y square and dxy, those are in xy plane. Those have x and y component. Now let us compare the interaction between dz square and dx square minus y square. Dz square lobes are majority along z-axis, so strong interaction, more repulsion. Energy will increase or decrease? Energy will increase. Now next, dx square minus y square. Along x-axis only one ligand is there. From this direction of x-axis, no ligand is there. Along y-axis, no ligand is there. It makes angle 30 degree. Along y-axis, there is no ligand, but it makes angle 30 degree. So relative to dz square, here interaction is poor, interaction is less. So its energy will be less than that of the dz square. Let us talk about dxz and dyz orbitals. Dxz orbital, if I consider, it makes 45 degree angle to x-axis, but with ligand more than 45 degree. With ligand more than 45 degree, but with this z-axis ligand, it makes 45 degree angle. Same thing is for dyz orbital. It can make 45 degree angle at least with the ligand approach. What about dx square minus y square and dxy orbitals? While studying triangular arrangement, while studying coordination number 3, I told you total angular separation by 4 lobes is 120 degree. For 4 lobes 120 degree, each lobe 30 degree average. So 30 degree separation is by dx square minus y square and dxy orbitals, and 45 degree minimum separation is there by dxz and dyz orbitals. Where is less separation? In dx square minus y square and dxy. So energy of whom will be larger? Dx square minus y square and dxy. So see the energy sequence. Highest energy is dz square, experience strong repulsion. Then in order to maintain barycenter the same, near barycenter, energy of dx square minus y square and dxy orbitals. And below that, dxz and dyz orbitals are there. Is energy sequence for triangular bipyramidal coordination number 5 clear? Let us see other kind of arrangement for coordination number 5, that is a square pyramidal arrangement in next part. As a homework question for you, out of 5 d orbitals, which 2 orbitals do experience least repulsion in TBP arrangement, trigonal bipyramidal arrangement? The model for square pyramidal we can consider likewise. It is our x-axis towards you and towards me, y-axis, and upside z-axis. Only one ligand is there along z-axis. Basically we were considering 3 parts. One dz square, other dxz, dyz, and third dx square minus y square and dxy. But here dx square minus y square and dx separation occurs. Different interaction is there. How? That I explained to you. Let me consider dx square minus y square orbital. One lobe along positive axis, second lobe along negative x-axis, lobe along positive y-axis, one lobe along negative y-axis. So 4 lobes of dx square minus y square. Direct interaction, strong interaction. So its energy should be considerably higher. Let us think about dxy orbital. In dxy orbital, lobes are between x and y. Makes 45-degree angle, makes 45-degree angle, 45-degree angle, 45-degree angle. Average 45-degree separation is there. So among dx square minus y square and dxy, whose energy will be higher? Dx square minus y square orbital energy will be higher. It is a one logic. Let us compare now other, say dz square orbital. Now in dz square orbital, one ligand is there at least along z axis. It experiences strong interaction, and in dz square orbital, donut shape is there in xy plane. So donut shape also experience interaction. That z axis lobe also experience interaction. One of the lobe at least experience interaction. It is the case of dz square. And what about dxy? In case of dxy, lobes are making angle 45 degree. So if I compare dz square and dxy, who will experience more repulsion? Dz square will experience more repulsion, surprisingly. So energy of dz square will be higher than that of dxy. Highest is dx square minus y square. Then is dz square. Then should be the energy of dxy. How barycenter will be there, that I discuss. Next two orbitals are left, dxz and dyz. Dxz orbital makes 45-degree angle, 45-degree angle, 45-degree angle here. So 45-degree angle dxz and dyz do make, and dxy also makes 45-degree angle. So who will be of higher energy, or whether all will be of same energy? Pay proper attention. In case of dxy orbital, this lobe also experience 45-degree interaction. Lobes towards my left side also experience 45-degree interaction. Lobe towards your right side experience 45-degree interaction. Lobe towards my right side experience 45-degree interaction. Everywhere 45-degree interaction is there. What about dxz? In case of dxz, one lobe experience 45-degree interaction. What about this lobe? This lobe has no z component here, no? One side only 45 interaction. So relatively, dxz and dyz experience less interaction, so energy will be less. Interaction here is repulsive interaction. So among dxy and other set dxz and dyz, energy of dxy will be higher than that of the dxz. So what is our energy sequence now? Dx square minus y square, dz square, dxy, then dxz and dyz. See how the barycenter separation is there. Highest energy dx square minus y square, then dz square, then barycenter is there, equilibrium line is there, gravity is there. Below that dxy orbital, and below that dxz and dyz orbitals. That's the energy sequence. That's the separation for coordination number 5, having square pyramidal arrangement. Now last one arrangement left, that's the octahedral, that we will see in next part. As a homework, simple question: which orbital has highest energy in splitting diagram in case of square pyramid? Octahedral arrangement is simple one. Along x-axis, ligands are there. Along y-axis, ligands are there. Along z-axis, also ligands are there. So ligands are approaching along axis. The orbitals which have lobes along axis will be one category, and orbitals which have no lobes along axis, other category. Which orbitals have lobes along axis? dz square and dx square minus y square. Those are called axial orbitals. And other non-axial orbitals dxy, dyz and dxz. Among these two sets, which two sets? Axial and non-axial. Which kind of set will experience more interaction, strong interaction? Yes, axial orbitals. If I consider dx square minus y square orbital, then the lobes which are along x-axis and y-axis will experience strong interaction compared to dxy, where lobes are in between axes. Therefore, because of strong interaction, energy of those axial orbitals dz square and dx square minus y square will increase. See the energy level. dz square and dx square minus y square of higher energy. And in order to maintain barycenter the same, the energy for dxj, dyj and dxy is lower. That's a splitting in octahedral complexes.
One additional thing I inform to you, here in octahedral complexes you are finding non-axial orbitals are decreasing in energy compared to barycenter, compared to center of gravity, compared to energy of equilibrium. It doesn't mean there is a attraction between electrons of non-axial orbitals and ligand field. Certainly there is a repulsion, means overall there is an increase in energy for any orbital, but relatively, comparatively, with respect to spherically symmetric hypothetical field, we are arranging the orbitals, we are arranging the splitting diagram, we are arranging the energy levels for. So though dxy, dyj, dxz are of low energy, they are experiencing repulsion. Keep in mind. Now as a homework, simple question, just write number of axial orbitals do present in octahedral complexes. Only write number in comment box.